Hi, I'm Hyunjin Hwang, and I'm a PhD student from KAIST. Let me introduce our work, AHP, a hyperedge prediction algorithm that learns to negative sample. A hypergraph is a general form of the graph which can represent the group interactions among the multiple nodes. Hypergraphs have advantages over pairwise graphs in that they have stronger expressive power. Hypergraphs are useful in representing the datasets in many domains, such as collaborations of researchers, chemical reactions, and recipes. For example, suppose a bibliography dataset which contains a set of papers, each co-authored by one or more researchers. Then, we can represent it as a hypergraph as shown in the figure by grouping the authors by the papers. Predicting a new or unobserved hyperedge has many applications, including collaboration recommendation and chemical reactions. Consider a hypergraph for chemical reactions, where each node represents a molecule and each hyperedge represents the reaction between the 7 molecules. Then, predicting an unobserved hyperedge leads to finding an undiscovered chemical reaction. In our work, we focus on a hyperedge prediction task, which is usually formulated as a classification problem. Specifically, given a hypergraph and a hyperedge candidate, we classify whether the given candidate would form a hyperedge or not. Consider the hyperedge sample space in the figure, which is composed of all potential subsets of nodes. What you're interested in here is whether a given hyperedge candidate from this orange area would be in the blue dashed area, which we called our target set. However, the sample space of hyperedge candidate is vast. Specifically, the size of sample space is 2 to the number of nodes. For example, in a DBLP dataset with around 15,000 nodes, there exists practically infinite number of hyperedge candidates. Thus, sampling is inevitable in practice, and some heuristic methods have been used for this purpose. However, in this paper, we show that previous heuristic methods lead to poor generalization ability. Here, we list a common procedure of previous hyperedge prediction algorithms. Hyperedge prediction can be divided into 3 steps. First, we sample negative examples from the hypergraph using a heuristic sampling rule. Then, we classify the sample negative examples and positive examples with the hypergraph neural network model. Lastly, we calculate the classification loss and update the model. In our work, we propose a generator that learns to negative sampling instead of the heuristic rules. Our generator learns which nodes compose each negative example. Then, a discriminator is trained with the generated negative examples and positive examples. The generator and discriminator are trained together using the Wasserstein loss. We call our approach Adversarial hyperedge prediction, or AHP in short. We performed experiments on 6 real-world hypergraphs. Details are shown in the table. For the baselines, we use 3 state-of-the-art methods and 4 variants of our approach, AHP, which use heuristic sampling methods instead of a learnable generator. First, we highlight that the state-of-the-art methods have poor generalization ability. Here, we provide the predictive performance of the state-of-the-art methods, and our approach measured on 3 different test sets. You can see that the state-of-the-art methods show low performances or high variances in their performance. We summarize the predictive performance in all considered datasets. On average, our method, AHP, shows significantly better performance compared to the state-of-the-art methods and the variants of AHP. In conclusion, we observed that the heuristic sampling schemes limit the generalization ability of hyperedge prediction methods. To address this limitation, we propose AHP, which learns to negative sample and shows better generalization ability. As a result, AHP shows up to 28.2% better predictive performance than the state-of-the-art methods. Thank you for listening.